So this is ELC 131, Circuit Analysis 1, and today we're going to talk about Kirchhoff's laws. Now, Kirchhoff's first law is Kirchhoff's current law, which states that the current entering a point or node must leave that point. Now, we define a node as a junction of two or more components. So, in this simple circuit, we have a voltage source, Vs, and a resistor, R, and where the positive terminal of Vs connects to R is a node, and we'll refer to that as node A. And where the resistor R connects to the negative terminal of the voltage source is another node, and we'll refer to that as node B. Now, remember with our voltage source, the schematic symbol for the voltage source, the longest line represents the positive terminal and the shorter line represents the negative terminal. And from our previous discussions, we've seen that when we have a source of potential difference and we provide a path for current, that current will flow from positive to negative. In here, again, we describe current flow as conventional current flow. In other words, it flows from positive to negative. Now, some current will leave the voltage source, and we'll call that current Is for the source current. And that current enters node A. Now, some current will leave node A and flow through the resistor. We'll call that current IR. Now, the current flows through IR and enters node B, IR, not IB, and the current IR enters the node B, and some current leaves node B and flows back into the source. We'll call that current, of course, IS. Now, Kirchhoff's current law states that the current entering a point or a node must leave that point. So for this circuit, we can say simply that Is equals IR. And Kirchhoff's current law is really just the law of the conservation of charge in a system. And hopefully this sort of makes sense, that whatever electrons we have leaving the source have nowhere else to go but to go through the resistor. And after they go through the resistor, they go back into the voltage source at a point of a deficiency of electrons. Now, Kirchhoff's voltage law states that around any closed loop, the sum of the voltage differences, or the potential differences, must equal zero. So when we look at this circuit, we have a closed loop existing right here. Now, when we draw these closed loops, it doesn't matter where we start, doesn't matter the direction we go, but we have to go all the way around this loop. Now, we know that when we apply or connect this voltage source to this closed loop, that current's going to flow through the resistor, and when current flows through a resistive element, we see a difference in potential energy, a drop in energy across that resistive element. And we'll call that voltage difference, that potential difference, that voltage drop, VR. And note that I've assigned a polarity to that voltage drop, positive to negative, and this polarity is determined solely by the direction of current. current flows down through the resistor, so the voltage drop across the resistor, VR, will be positive to negative. Now, what we're going to do is just simply travel around this closed loop and add up the potential differences. And these potential differences should or must add up to 0. So, we start here, and the first thing we encounter is a rise in potential energy, right? There's a rise in voltage. The voltage is from negative to positive. So I'm going to record this as plus Vs. Now, as I continue around this closed loop, we come to a positive to negative difference across the resistor R. VR is a drop in voltage, so I'm going to record this as minus VR. And if I rearrange this equation, I end up with Vs equaling VR. And this hopefully makes sense. This is really just the conservation of energy. Vs is potential energy, VR is kinetic energy, and we know whatever energy we apply to a system has to be used up somewhere in that system